we have, over the last many decades, made a cosmological model that really seems to explain a lot of things that we observe in our universe. We have been able to cover, the Big Bang, the CMB that we can go into. We have the formation of structures, the formation of stars. And yet there seems to be some problems. There seems to be a reason to rethink cosmology. And you've been spending quite a lot of years to finding problems in this lambda CDM model that we refer to. Can you tell us more about why we need to rethink this model that seems to be working so well?
Sure. So our knowledge of the universe is actually restricted to a rather finite range of times or temperatures or energies. From the present back to a time when the temperature of the universe was about that in the center of the sun, which is a very long range of temperature, around a few degrees above absolute zero now, to temperatures that you get at the center of the sun, millions of degrees Kelvin. However, when we talk about the Big Bang and how it all started, we need to go much farther back in time, over a range of time and a range of temperatures about which we actually have no evidence. And so the simplest thing that people have done is simply to say, whatever equations I use to describe the part where I am able to explain observations in which I can make observations.
And that is like the universe that we see around us, the galaxies, the laws of physics that we can test here in laboratories and stuff.
Right, so there's things we can test either in the laboratory or looking out in space as far as we can see. All that fits well with a certain set of equations, but it's a gross assumption to say those same equations continue going back in time. And going back in time means the universe is becoming more and more condensed, higher density, higher temperatures, reaching scales which we've never tested in the laboratory before. Not a small stretch, but a stretch of something like 60 orders of magnitude in density is how far back you have to go before you get to the so-called Big Bang.
And just to understand, those are temperatures and energies that we cannot even reach with LHC, like the collider experiments.
Not even close.
We are going very, very back in time where the energy was much, much higher.
Right. And that's the first thing you should be concerned about, a reason why you might have to think more carefully about this untested region. A second reason is when we observe the universe today, for example, the microwave background, we observe that on large scales it's remarkably homogeneous, uniform, smooth distribution of energy. It has a very low entropy, a very small amount of disorder in it. It has a special arrangement of entropy or order and disorder in it. There's a lot of disorder in the matter, but the space-time seems to be remarkably smooth.
So when you're saying things are very smooth, around here, around us is certainly not smooth, and we look at and we see galaxies and clump.
Right.
But you're saying on cosmological scales, like really big scales, these are just tiny, small perturbations, which is defined as smooth. Is that?
Well, it's even stronger statement than that, because what we're really doing when we look at the microwave background is not getting a snapshot of what the universe looks like now, or even here. We're getting a snapshot of what it looks like some distance away, long time ago. Now, whatever it was there then, if the universe is smooth, should be similar conditions here. So at that time, there was not only smoothness on large scales, but even smoothness on the scales of the stuff in this room. All the atoms in this room, which form clumps, were then boiled into a hot gas that was very uniformly spread. And it's over time, between then and now, over roughly a period of 13.8 billion years, that smooth universe, or nearly perfectly smooth universe, turned into a universe that has lumps on small scales, including planets, people, stars, galaxies, etc. So we're getting a picture of what things were like in the past. So somehow we began with a universe with very special conditions. And by special, I mean, we think everything is described by Einstein's theory of general relativity, going back in time. But in Einstein's theory, the last thing you expect is a universe which is uniform and smooth. Because in Einstein's theory, space is elastic, like a kind of rubbery jello. And it should be able to curve and warp and contract in some places and expand in others. It should be very uneven. But something must have happened in the early universe, in this untested period, or maybe before that untested period, that took what would generally be something very different and turned it into something very special. Nature has given us a huge hint. This homogeneity or smoothness that we're talking about is a huge hint, because it's not something that occurs naturally in gravity. It requires some new physics, some novel physics, to create that condition. And nature is telling us that something like that happened, and we wouldn't exist without it.
So if I'm taking the normal cosmological models,
yes,
and try to apply them and say, well, I need the universe to be very, very smooth.
Yes.
Does it imply that I have to be extremely fine-tuned at very early times? I have to put in numbers for the matter density and so forth that are so fine-tuned that cannot be the answer? Then that will hint that there has to be something else that is generating that smoothness, and that's what you have been thinking about.
Exactly.
Right? Yeah.
So we start with the idea of the Big Bang. So if you just naively extrapolate back and say, I'm just going to assume those equations apply even where I can't test them, I discover the universe converges to, everything in the universe, space, time, matter, and energy, converges to a point, which we call the cosmic singularity, or it's more commonly going forward in time called the Big Bang. Coming out of the Big Bang, what we expect is that there'll be various effects, including large effects of quantum physics and gravity, which are disrupting everything, making everything as messy, curved, warped as you can possibly imagine. And if that were the full story, you should see that the universe in the large scales today, or in the microwave background, should have remnants of that huge non-smoothness, that unevenness. It should be everywhere evident. But we see the opposite. We see this incredible smoothness. So cosmologists realized that back in the 1980s, and they thought, okay, we'll try to patch this Big Bang picture by putting something after the bang that will take the mess created out of the bang and turn it into smoothness. And the idea they had was there was a period of extraordinary rapid expansion, accelerated expansion, which stretched the universe ultra fast, taking what would have been an irregular universe, and the idea was making it into something smooth, consistent with what we observe. And this phenomenon is referred to as inflation. So many astrophysicists and cosmologists today believe that a Big Bang followed by a period of inflation, all occurring in a period well before what we can test in the laboratory, had to have occurred to explain what we observe. But does the idea actually work? That's the question that I've been asking. Does this inflationary phenomenon work? And if it doesn't, is it unique? Are there other things that could also explain it?
And is there?
Well, first of all, let's ask if it works. We thought inflation worked for many years, but what we've shown in recent years is that there's various things that we didn't understand about inflation and general relativity that lead to the conclusion that actually it doesn't work after all. So we thought it did based on how could that happen? You may wonder, how does something like that happen? It happens because general relativity is actually a very hard theory to do mathematical computations with on pencil and paper. So if you ask, given some very non-uniform universe, how is it going to change with time? We never really could calculate that with pencil and paper. We had analogies about stretching the universe that made us think it would lead to smoothing. But we should have worried that, in fact, if you make something non-smooth in general relativity, all that non-smoothness of space-time itself carries energy and induces forces that could be resisting something like inflation taking place. So what we really needed to do was find a way of actually solving Einstein's equations, beginning from a very non-uniform universe, to see well, does it smooth it
If it
out or
actually
doesn't
works,
it?
yeah, exactly.
Yeah. And what we discovered using now recently developed techniques for solving Einstein's equations on a computer, which is an enormous challenge, very different than solving other kinds of problems on computers. What we found recently is it actually doesn't work.
So you actually took, tried to simulate something that would, mimic, a universe with perturbations, and then you impose some inflationary, expansion to it, and how did you see that it didn't work?
You can see it doesn't work numerically because when you visualize the distribution of matter and energy, you begin with a distribution which is very uneven, which is supposed to represent the condition you expected coming out of the Big Bang. And then you ask the question, does it become smooth or not?
Yeah, exactly.
And if anything, it does the opposite. It becomes more unsmooth, essentially because the wrinkles in space-time tend to close in on themselves and form even bigger wrinkles and bigger deviations from smoothness over time. So you can't even call them perturbations. These are huge deviations from smoothness that your eye can't miss, and which are completely inconsistent with what we observe, for example, in the microwave background. So then you could ask the question, is there another approach? And so interestingly, there is another approach that can work, but it has its own interesting implications. And the idea is that if the universe contracts, but in what we call a slow way, in which the contraction is extremely slow compared to what's happening to what we call the Hubble radius, which is the region of space an observer can see at a given time. So, what happens in this case is the region of space around you that you can observe in this contracting universe is very rapidly closing in on you. The space itself is hardly contracting at all. So you see less and less space as time goes on. Within the part of space you can see, the universe ends up looking more and more smooth. And even beyond it, it looks more and more smooth. At first we thought it was just what the observer sees, but we discovered recently it's a much stronger effect. Every place in space begins to do the same thing, falls into sync and smooths at virtually, within a very short range of time, smooths to the same condition. Even two regions that are out of causal contact, there's too far away for light or other information to connect them. Even such regions independently smooth themselves and smooth to the same condition as the region far away.
So let me understand, so are they, is it only smooth within your own horizon, or is it smooth, everywhere? Now you're saying is, smooth in each patch here.
So so it's a combination of two things.
It must be a combination, yeah.
Yeah, so if we were following one region, the region around you, you'd find that it smooths. Yeah. If you were able to communicate, if you were able to discover what is happening over here, the same thing is happening over here. But the interesting thing is they're smoothing to the same condition, and same with every point in between. So suddenly you have
means like the whole
universe is smoothing. It's a universal smoother. So we thought until recently this was impossible.
Because things cannot talk to each other, right?
We thought in order to smooth the universe, you need to get regions to talk to one another first, smooth themselves out, and then imagine stretching it. But that turns out to be the wrong way to do it.
But that is the way when you think about the Big Bang, and that's how the inflationary picture tries to solve it, right? Things are first causally connected, and then you stretch it. That's the explanation. But here you're saying, well, it might actually be working the other way around if you have a contraction instead. Is that?
Yeah, so it's exactly the opposite. Yeah. It says first you want to separate everybody so they're out of communication, but they are following the same equations. So because they're following the same equations, they're going to follow similar paths. And if the equations happen to have what we call an attractor behavior, they'll actually end up in the same place, namely smooth within and smooth with respect to one another. So suddenly regions which were not in causal contact, which were too far separated to communicate with one another, are independently doing the same thing and falling into sync. It's an amazing thing which we didn't think, which we never imagined was possible before, but it comes out of general relativity. It was sitting there all the time to be discovered. But theorists were so focused on Big Bang and expanding universes, they just didn't think much about contracting universes. And I include myself in that number.
but contracting universes you don't see, so that's, I mean, a natural reason why you don't think about it, right? But you believe, or part of your cosmology says that there might be a contracting period before what we call the Big Bang. Is that correctly understood?
That's correct.
That's how you put it together.
So again, we're following a line of reasoning. Yeah. So what we're saying is, okay, there's something interesting about this slow contraction, which is it does something which is not possible during any kind of expansion. It's actually able to smooth the universe everywhere. Not just what we see, but even beyond what we see. Now, we live in a universe which is smooth. Yeah. That's a pretty strong reason for believing that slow contraction is the cause of that effect, because it's the only example we know at the present time that can really smooth the universe. Yeah. Inflation fails, Big Bang fails, Big Bang plus inflation fails. Yeah. So contraction succeeds. Now, we live in an expanding universe, not a contracting universe. And we don't want to have our contracting universe, which is nice and smooth, spoiled by large quantum effects that mess up the smoothness we work so hard to create. So what do we want to do? We want to have a universe which only contracts for a short period of time and then transitions smoothly to an expanding universe. And we call that transition a bounce. So there are different effects that can cause a contraction to convert to an expansion, which we also study. We have different examples of different kinds of theories that can produce just the bounce portion of this period. And when they're producing the bounce, they can also convert the energy that was originally causing the contraction into expansion plus the matter and radiation that we observe in the universe today. So you end up coming out of the bounce not just with expansion, but with a hot universe, a universe full of matter and radiation.
And all the particles and the fluctuations that we see today.
Yeah, all that stuff, all those things that you want, that we observe when we get to temperatures of the sun and smaller in the universe, are all laid in place.
Part of that, yeah.
Yeah, it's all part of the story.
So the contraction phase, like if you then start to think backwards from that phase, it means that the universe would have been greater and greater and greater in the
could have even been infinite.
It could have been infinite, and then it went through that bounce.
Right.
Yeah. So is it? This does not imply like a cyclic model. That is, of course, what comes to your mind. Is like, why is it that we are living in such a special time where we experience the universe right after this only bounce that it had, for infinitely long time. It was infinitely big. Suddenly it happened, and now we're sitting here. It could naturally be that is something that's happened periodically. So we're not in a special situation. So are there ways to?
Yeah, I think that's very sound reasoning. I personally don't like the idea of one-time events, one-time phenomena occurring in the universe.
No.
In fact, that's one thing that disturbs me about the Big Bang. There's a Big Bang. It's a one-time event. And we see no example of it afterwards, okay? So the bounce, there's no reason why it should happen only once in the universe. It could happen more than once. It could even happen in such a way that it's periodic, cyclical, that you're describing. And it can happen in such a way that it's stable, cyclically, and continues arbitrarily far in the past and arbitrarily far in the future.
Is there a way to test this? Like, I mean, you can imagine that something from the previous epoch is carried, like a little bit is carried into the next universe, and maybe you can see some perturbations that is left over or something like that.
It's a good question.
Is there something?
So at the moment we don't know of anything, except but let me be a little more careful. So there is something that is carried over from the previous cycle, the smoothness and flatness and perturbations in the distribution of matter were all created during the slow contraction that preceded the last bounce, what we thought of before up till now as the bang. It would have been the most recent bounce. All that is carried forward to the present. But something that happens during slow contraction is the amount of space you observe when the contraction begins. Let's say contraction began right now. Okay, so about 40 billion light years is the size of the universe that we can see at the present time. That region would contract to a microscopic scale. Most of that stuff would disappear outside the region we could see up to the time of the bounce. What we call the Hubble radius, the distance you could see would have shrunk by that much. After the bounce, we create new matter and radiation. The Hubble radius grows, but the stuff that was there before, we cannot see within our Hubble radius because it's expanding apart from us along with the Hubble radius. So you lose track of it. So in a sense, you lose memory of earlier cycles every time you go through one of these contractions and bounces.
Because it's being taken out of your horizon, basically.
Right. So the total amount of space is growing. So it could even begin with an infinite amount of space, but it keeps growing by some factor, for example, or there could be a finite amount of space, but it keeps growing by some factor. But you only see a little patch of it, depending upon how many bounces you've had in your past up to that point, how much stuff you've lost sight of from cycle to cycle. So, for example, we have black holes that we observe in our present universe. If the contraction were to begin now, by the time the bounce occurred, we as observers would not be able to see any of those black holes. They would be outside our Hubble radius. After the bounce, they'd be spreading out from each other and us. We would have lost sight of those black holes.
And there's not even a chance that there is something left over just because that we are left in such a small...
In terms of the black holes, we can actually do the calculation because we know how many there are. And the answer is no. But that doesn't mean there couldn't be, there might not be something. So now we can get a little science fiction-y here. So up till now, when people thought about bounces, when cosmologists thought of bounces, they assumed the contraction had to occur all the way to zero size and then out to
then you of course lose everything.
Then you lose everything.
Might not happen.
Right, but actually in the kinds of scenarios we're thinking about now, because we want to preserve the smoothness, we want to make sure the universe bounces well before you get to such high densities. You don't need to contract that much to smooth the universe sufficiently or to flatten it and create the other properties you need. So once you've created what you need, why not bounce then? In that case, there's nothing funny or singular or black hole-like or anything bad happening to space-time. It's as regular as the space in this room. And there's no reason, if I were sitting on the other side of that bounce, I couldn't send signals through. Now, some of those signals would be wiped out because if I sent, for example, a rock or particles through there, when the energy of the slow contraction was converted to new matter and radiation, heated up, it would melt that stuff
and scatter
it away.
Like
But something like a gravitational wave, you could. I could send signals from my end, explaining everything I had learned over the course of my cycle. Watch out for that bounce that's going to occur a certain time from now. And in principle, if you were in the right place in the right time with respect to me, there's nothing to stop you from receiving that signal.
So if we go and think about the observation of these maybe primordial gravitational waves, is that one way of probing this? Or are there other ways of maybe ruling out your model?
So inflation produces, after the bang, a spectrum of gravitational waves. You don't get that in slow contraction. So right now, scientists around the world are working very hard to develop observatories that can look for the primordial gravitational waves you would get in Big Bang inflation.
And just to understand, those waves are not at all, similar to the waves that we have just seen, with LIGO and stuff. They are much larger scales.
Correct.
So you're going to use, is that true, like the CMB?
Yes.
Basically that as the background and looking at how...
Yeah, you're looking at how those waves distort the microwave background by producing certain polarization patterns in them. So that's what they're trying to do.
So that's one way of ruling that out?
And we would say if you see that, that would be inconsistent with the slow contraction picture because that does not produce that effect.
But you cannot turn it around, right? Like if you don't see them, you can rule out inflation because you might not even know what scale they are with inflation.
The problem with inflation these days that we've learned about inflation is it's actually a totally non-predictive theory, in the sense that it's not that it changes the universe from disordered to ordered. It actually produces what we call a multiverse of possibilities. It turns space-time, even if it were perfectly smooth, a period of inflation due to quantum effects turns the universe into infinitely many patches, which have every degree of non-smoothness and non-curvature and anything, elephants and whatever else you can imagine, will occur in some place in this multiverse. And in fact, they will occur an infinite number of times. That would include anything you might conceivably observe, okay? But that means that there's no way to falsify such a theory as that, because anything you observe, you could argue, would have to have occurred someplace in the multiverse. If you can observe it, then the multiverse, everything that can happen will happen. It will happen an infinite number of times. But that means that you can't verify such a theory. You can't falsify such a theory. So if you look for these gravitational waves and you don't find them, some inflationary theorists will say, "Oh, we must live in a patch."
It's just because the number should have been smaller for this model or that.
Right.
Or
not even the model. They'll just say in the multiverse, we happen to live in a region where you happen not to form them, and that's possible too. So, because everything is possible, that's possible too.
Yeah, exactly.
So I think the problem with the Big Bang and adding the inflation to the Big Bang theory is that instead of becoming a highly predictive theory, which explained why the universe was smooth and flat and why the fluctuations in the microwave background are as we observe them, the theory sort of dissolved itself or ate itself when we properly understood how quantum physics combined with inflation works and general relativity works. We discovered, inflation, what it really does is it creates this multitude of everything. And it's kind of led to an interesting philosophical or psychological split in scientific thinking, because in conventional thinking, scientific thinking, we would say, well, this theory is non-predictive, it's non-falsifiable, it's outside the realm of normal science. Because a condition of a good scientific theory is there should exist a test, or more, at least one test, but one or more tests, that if you do the experiment and you find the opposite of that,
you rule it out.
You rule it out.
Yeah.
But in this case, anything you could imagine measuring, the opposite of that measurement is also predicted in the multiverse. So there is no way of ruling it out. So so we've kind of run into this problem that the theory is broken down from its own foundations, not the usual way a theory breaks down, not because we made an observation and said that contradicted it, but because it turned out it produces this ultra multiplicity of outcomes. And we do not have that problem, we don't have that issue in the slow contraction bouncing universe.